Hi everyone, my name is Patrick Mendoza, and today I'll be going over my Serve 2023 experience. Who am I? Well, to reiterate, my name is Patrick Mendoza. I was born and raised in Miami Beach, Florida, and I am currently a rising second year at UC Berkeley, where I major in electrical engineering and computer sciences, as well as a minor in applied mathematics. My research this summer was at the Rising Lab, directed by Dr. Sendip Ray, working on secure, accessible, and sustainable transportation research funded by the NSF, alongside guidance and mentorship from graduate students Tashfiq and Derek. As you can see, there they are, all three of them at the Rising Lab. Um, the objectives I had for my specific project this summer was to develop software to simulate connected and autonomous vehicle trajectories in reduced speed work zones based on sensory data and V2I communications. Well, reduced speed work zones are work zones that you can see on an everyday basis. For example, construction happening on a highway or during a school zone, in the morning. These are examples of reduced speed work zones where a vehicle has to adjust to the specified speed limit in that area. And V2I stands for Vehicle to Infrastructure Communication. This is where infrastructure passes information to the vehicle, and the vehicle, based on that data, should ensue some sort of action, whether it be speed up or reduce the speed, for example, in work zones. We're also looking to simulate various attack methodologies for these trajectories, as well as exploring new approaches and building resilience toward V2I and V2X malicious communications. Uh, Examples of this are signal jamming and spoofing. The timeline that we had for this project was obviously our first week was to define objectives, deadlines, and goals for the project. The second week, we read up on the literature of uh, connected and autonomous vehicle security and trajectories based on sensory data. The third and fourth week, we started designing how we would approach our goal of figuring out how to simulate these attacks and the trajectories of the connected autonomous vehicle. The fifth and sixth week, after some thorough planning and of how we were going to implement this, we went ahead and started implementing this into tangible code. The seventh and eighth week, after our trajectory was implemented, we started exploring various attacks on the CAV. For example, uh, and V2I communication, something resembling a V2I communication may be the distance to the work zone, the length of the work zone, and the speed limit in the work zone. An example of attack would be assume that the ground truth to the distance of the work zone is 100 meters, and some malicious communication could say that the work zone is 200 meters. That 100-meter discrepancy could have many consequences, and this is one example of how malicious communication could happen, on a trajectory of a CAV. And finally, the last this week and next week, what we'll be trying to discover is how to detect this type of malicious V2I communication. And the overview of this project was we created a CAV object that utilizes a pseudo-random rule-based approach to generate predictable yet random trajectories. Having a pseudo-random approach allowed for us to generate many types of trajectories without having to specifically hard code any sort of trajectory. And we gave us a lot of versatility to see different scenarios that we could try to extrapolate to a real life CAV trajectory. Additionally, we integrated V2I communications such as reduce speed and stop to mimic real world circumstances in the CAV trajectory. During our design process, we broke down the trajectory into three phases: the acceleration phase, the random trajectory phase, and the deceleration phase. And currently, we are exploring and developing ways to detect malicious and faulty V2I communications during a CAV's trajectory to make autonomous vehicles more robust to signal jamming and signal spoofing, which are examples of malicious communications. You can see to the right, we have a graph generated from one of the trajectories of our CAV, where two V2I communications were passed into the vehicle. As you can see at around 115 seconds, you can see that the stop was a communication passed into the vehicle where it stopped for some duration of time. And around 230 seconds, we can see that our vehicle is in a work zone for some specific duration, cruising at approximately 10 meters per second. And everywhere around that, you would see this is some randomness associated with the trajectory, and the the beginning here and the end, or the end here and the beginning, represent the acceleration and deceleration phase respectively. And below that, we can actually see the mathematical representation of our CAV design, where from 0 to some tau less than s, or from some 0 to some s tau, we have the acceleration phase. From s tau to some tau less than k tau, that represents the random trajectory phase, and the k tau all the way to n represents the deceleration phase. I would also like to mention that tau represents the time step of our trajectory. For example, tau equals 1 represents that we're going to sample our information of our trajectory of our vehicle every second, and tau just represents the sampling rate um, of our vehicle and the information we gather from it. I want to acknowledge many of the staff, the faculty in the institution where I was uh, welcomed to this summer was the University of Florida. I would like to also thank the National Science Foundation, the Rising Lab, Warren B. Nelms Institute, Tashfiq and Derek for providing me with great advice, information, and perspective into the project I was working on this summer, and obviously the friends that I made throughout the summer at the Rising Lab. Again, thank you so much for providing me with such an insightful and wonderful summer research experience.